What's going on, class? Dr. Nee here. Today is lecture number 5, and we're going to get into axial load and axial deformation. I'm sorry, axial load and deformation. We're going to dig into that today. Got a number of example problems to walk you through, and I think that should give you a good way to understand this particular concept. But first, let's look over here at our screen share here. We have a picture starting things out of this drill pipe stacked on this oil rig. And these type of structures are subject to large deformations because as they're drilling, there is a axial force applied to the end of this rig, right? And what happens is this force causes deformation in part or even elastically to its structure. And so what we're going to show you here is that whenever you have an axial load applied to a member, applied to a pole, to a beam, or what have you, there actually is a distribution of how that axial load is distributed along the length of the member. So take a look right here where P is our axial load. You would see by looking at these horizontal lines that are drawn on this member that by the applied force, there's actually a distortion of these horizontal lines. If you look at A, it distorts. However, it changes, or the amount of distortion changes as you go further down away from the applied force. So B actually distorts slightly less than A. And at some particular distance, some distance away from the load, these lines no longer distort, and they begin to then deform equally along the length. And so lines located away from the load support, they remain straight. And then also towards the end, when there is a fixed end, load distort lines, the load begins to distort the lines once again as they're located near the support. So what's happening is that there is a uniform displacement that we can think about, or there is also a localized displacement where it changes depending on where you are in position to where the load is applied. Here's an actual physical representation by showing us another coupon specimen, a rubber coupon specimen that is with lines drawn on it. You see again close to the supports where the load is applied. Typically, these devices only move up, right? The top grip moves up. You see that the lines are distorted and how it's applied, these grips here. But towards the middle, the lines remain straight. Here's another example. After it's stretched, localized distortion at the grips smooth out. They smooth out after they're stretched. And this is called the St. Vincent's principle, the St. Vincent's principle. Here's another practical example of members that can be experiencing this axial load and axial deformation. Here are walkways in a mall where you see these rods right here, A, B, C, right? There's vertical displacement at the top floor, B, right? Because there's a force being applied there. And then also there's a displacement at the bottom floor here at C. And it all depends on the force, right? We want to keep this in mind. It's going to depend on the force that's being applied at that particular location. It's also going to depend on the length of the rod at that particular location. And then other things that also matter is the area, the cross-section or area of that member, as well as the modulus of elasticity of that material. All right, of that material. So take a look. Let's come back over here to our document cam. All right, so here are the things that we want to keep in mind, right? First of all, let me go ahead and give you another visual. I'll give you another visual when it comes to a rod or a beam or a bar being displaced. This is consider our original length. Let's just say this is a cantilever. Our original length, L sub naught. Make sure you all can see that clearly. Boom. All right, original length. However, when a load is applied, a load P, there is a slight increase of the length happening at the place that the load is applied, so that the new length, we can just call this L. And this amount here is going to be represented by this Greek letter that we've seen before, delta, right? And this is the displacement. This is displacement. And as I just said before I started drawing that, this has a determination that, or depends on a number of things. It's going to depend on the load at the location. And remember that this load can be represented as N or F as well. It's going to depend on the length. It's going to also depend on the cross-section or area, which sometimes is consistent. We started off looking at a consistent cross-sectional area, but things are going to change and you're going to see that. And then the material, or the modulus of elasticity, more specifically, more specifically, elastic modulus. All right. So here's how it would look in theory, right? When things are all subject to change, a safe way of writing this would be the displacement. The relative displacement is the integral over the length from 0 to L of N, or the force, the load, rather, that's applied as it changes with respect to X. dx represents the change along the length, so there's your length there, over ax, how the area changes, over ex, how the material changes. Now, obviously things get a lot simpler when these things stay constant, when the cross-sectional area stay constant, also when E stays constant. And then when we can just identify a single concentrated load for whatever we're trying to determine, we can rewrite this as equal to the summation of N L over AE. Right? That's when we're not having any type of changes in terms of an equation along the length, but still it's just a lot of different concentrated loads. The area is localized or constant for that particular location. And then the material also can be determined as a single value for that location. So this is the summation. This is when we're adding up multiple. And then there are other cases where it can also be just simply determined by NL over AE. And I'm going to put a square on that one because that's what I want you to keep in mind. The summation is going to come into effect when you're talking about different places that loads are applied and you're trying to get it all the way through. But ultimately, you want to get what we call the relative, or be familiar with finding the relative displacement. And let me see if I can help you understand that really quick, right? The relative displacement. So imagine if we had, again, another bar, that's a cantilever. And we have a load being applied right here, right? And let's just call this point right here A, the NA. And then we have another load apply right here. Let's call that B. And then we have another load here. Let's call that C. And then let's call the fixed end D. Well, as we know that each of these loads are going to call, in this elastic material, cause a displacement, right? A displacement. And as I started this chapter off, or this lecture off, telling you that the amount of displacement actually varies locally along. And at the point of the applied load, there is going to be a noticeable displacement. But this placement, the change in the location of A, so it'll move from A to, let's call this new location A prime, right? It's going to move from here to here. That is going to be a certain value compared to B, which will be different than the amount of change that happens compared to C. Why? Because it varies along the length. And so what we will be able to do is cut this in between our points. We'll be able to cut this in between our points to where we can add up. We can add up the displacement if we want to know the total displacement by summing all of the forces. See, these are ends. This is the end load. This is the end load. Over the respective length of their cut, over the cross-sectional area of their cut, over the modulus of elasticity of that particular material at that location. So if we're just looking at this particular part right here, what we will call this is the displacement of A, location A, relative to B. A relative to B. Because we're not talking about A relative to D, because A relative to D would get all this into account. This one right here, if we want to look at the displacement between B and this would be the displacement of B relative to C. And then here we would get the displacement of C relative to D. And in order to get the displacement of A relative to D, we would essentially be adding up the intermediate displacements of all the individual sections at which loads are applied. That is what this means here. That is what this means here. And what we're gonna show you as we move forward is that things can change, right? Sometimes you may have a bar that has one cross-sectional diameter, and then it gets narrow. And loads can be applied here. A load can be applied here. And it's going to become a necessity to be able to figure out and visualize where things need to be cut so that you can determine how to break up your summation of displacements, whether you're trying to find a displacement across the entire length or you're just trying to find a displacement of one point relative to the other point. So without further ado, what we're going to do is go ahead and jump into some examples to help illustrate this. I think that's the best way because a number of these things would just be a matter of getting used to being able to see or getting used to seeing where you should cut and how you should represent what you see in the equations of relative displacement. Let's look at this screen share here. The first one we're going to look at is problem number 4-2. 4-2 is what we're going to be doing as our first example. That's our first example. And the problem statement says to us, it says that a copper shaft is subject to the axial load shown. Determine the displacement of the NA, here's NA, with respect to D. Find the displacement of A with respect to D if the diameters of each segment are DAB equal 0.75 inches, DBC is 1 inch, and then CD is 0.5 inches of diameter. It also gives us the modulus of elasticity, calling it copper, of 18,000 KSI, 18,000 KSI. So changing this view a little bit, what we're going to do with our particular diagram here or our bar, see if I have one on a sheet of paper that I can maybe show you a little bit, is the first thing we're going to cut in between the discontinuities, right? So let me draw this in full really quick. I'm going to draw this in full. This is the first part. Then it gets a lot wider. Then it gets a lot narrower here at the end, right? Well, what we're going to do is we're going to cut it here before it gets to this change in diameter. We're going to cut it here at this new diameter. And then we're also going to cut it here such that in order to determine the displacement of A with respect to D, D is on this side, A is on this side, we're going to need to sum up the relative displacements along the length. of this bar. So NL over AE. So first and foremost, let's first draw this first cut. Well, if we look at our image, we would see that there is an applied force here of 8 kips. And so by equilibrium, what would be the internal load as a result of this applied load? The internal load, since it's not moving, is a static condition. Equilibrium tells us that we will also have an 8K here in this case, an 8K. Is everybody with me on that? All right. So we're going to keep that there. Let me go ahead and draw this while we're here. Let's draw the second part of the cut. Boom. And we're cutting halfway through there. This is 8K according to our diagram. It also shows that we have another 2 instances of 5K being applied on both sides of these. 5K. And so what does equilibrium tell us? We got 8K going in this direction. And then we got another 10K, 5 and 5 going in that direction. So in order for this to be in equilibrium, we would have to have another 2K going in this direction. Another 2K going in this direction. Now, lastly, I'm going to draw this last part. But in truth, we don't have to draw the whole thing. We could actually come from this side and just draw here, because we just want to get the internal. We want to get the internal force there. And we know on the outside, there is a 6K. A 6K. So that means internally right here, there is another 6K in order to make it at equilibrium. So let's start out using our equations so that we can add this all together. First, in this case, we're going to have P or N, right? NLAE. That's the displacement. So what is N in this case? Well, N internally is going to be a -8. L represents the length of that portion that we cut. So the length of this part right here, according to our diagram, if we look at it, is 80 inches. It's 80 inches. So we're going to say that L is 80, keeping it in inches. A, what is A? A is the cross-sectional area. According to our problem statement, the cross-sectional area of DAB is 0.75 inches. 0.75 inches. We want it in square inches. So we're going to go ahead and do the equation. Pi d squared, which is 0.75 inches. Pi d squared over 4. Pi d squared over 4. And then E was given to us already, which was 18 for copper, 18 times 10 to the 3. Cool. So we can solve for that. When we come back to it, let's go ahead and write out the other ones. Internally here, we have a 2 going in this direction internally. So this is going to be 2. What is the length? What is the length of this middle portion here, right, that we cut? Well, the length of that is 150. 150. So this is going to be 150. The area in this case is, again, the equation pi d is 1. Pi d squared over 4. And then E is 18 times 10 to the 3. Lastly, we're going to come back and do the math behind all these. Lastly, we're going to come over here, and the internal load in this case is 6. But because we're going to the other direction, we're going to change our sign. So ordinarily, this would be a -6. because we're going the other direction, we're going to go ahead and multiply it times another direction because we want to be consistent, right? If we were going the other direction, we would have kept the negative sign. But because now we're looking at it from the other side, we're going to change the sign. The length of that section is 100. The area, pi d 0.5 squared over 4. And then the area or the modulus of elasticity remains the same, 18 times 10 to the 3. Right? So there we are. What we're going to do is add these up. We're going to add these up as we prepare to solve for this problem. So first one, -8 times. Make sure you all can follow along. And I recommend you doing this. I want to do this in real time and not cut it or anything because it gives you opportunity to do it as well. Times 0.75 squared, 4. Times 10 to the 3. All right, so here's what I have. For this one, I have 0.08048. Over here, 2 times 150. Pi times 1 squared 4 times 18 to 3. Here we have 0.0212. And then down here, 6 times 100. Squared divided by 4 times 18. And here we have, what I have is 0.16976. So we're going to add these up together, calling this the displacement of A with respect to D. We have negative 0.08048 plus 0.02122 plus 0.16976. Add these up together. The answer I have is 0.1105. Right? This could just be round up if you're doing 3 decimal places to 0.111. What is that? That is in inches. Do you concur? Do you concur? Let me know if your calculations, if you can, your calculations agree with that. But that will be the answer for this particular problem. Again, what we did was we were asked to find the relative displacement of A with respect to D. If you look at it, you would have saw that this was considered B here. This was considered C. And in order to get A with respect to B, as it asked us, we needed to summate or add up all of the relative displacements along the way by using NL over AE. We added it up, and this is the value we got. All right, cool. So let's keep it moving, y'all. Our next problem that we're going to look at, that's going to give us an opportunity to examine another concept that you'll see in a moment, is 4-21. 4-21. And I'm going to try to show you a little bit more so you all can see how this is written in the problem statement, right? So here it is. It says here 4-21, the rigid beam is supported at its ends by two A36 tie rods, steel tie rods. If the allowable stress for the steel, stress allowable, we're going to integrate a couple of concepts, is 16.2 KSI, the load W here, distributed load, is 3 kips per foot, and X, the distance or the length of the distributed load, is 4 feet. Determine, it asks us, the smallest diameter of each rod so that the beam remains in a horizontal position. A lot of this is important. The horizontal position is important. The smallest diameter is important. We're going to have to do a number of things, and I intend to walk you through that right now. So let me come back over here and show you what we're doing on our paper. I'm going to seek to line up the image so you all can see it very conveniently on the screen. Boom, there we go. All right, so here's the image. Now, the first thing we need to do is determine what kind of forces are in the rods. And to kick things off with that, we're going to do our equilibrium equations of the whole thing. So if we sum the forces in the y direction, right, for this entire thing, we could say that F, free body diagram, right? Free body diagram. We got F, A, B here. On this side, we got F, C, D. And then obviously there's a distributed load here. The resultant of this distributed load is going to take place in the middle of this rectangular distribution. And it gave us that W is equal to 3 and the length is equal to 4. So that's going to be 3 times 4 kips. So over here, coming back to some of the forces in the y direction, you got FAB minus 3 times 4 plus FCD, right? And that's going to be set equal to 0. That's one equation. The next equation we can solve for is by summing the moments about A. Sum of the moments about A to solve for the unknown. So in this case, we got 12, 3 times 4. If this was our positive convention, we got 3 times 4. This is going to create a negative moment. So negative 3 times 4, which is 12, times the distance here. If this whole thing was 4, this distance will be 2. So times 2 plus the distance of FCD. Well, the overall length is 8. So force FCD times distance 8 equals 0. And from there, we can solve that FCD is equal to 3 kips. And we can use those 3 kips to then come back into our original equation with the sum forces in the y and determine that FAB is equal to 9 kips. All right, so those are some of the basic things we were able to solve for FAB, and we were able to solve for FCD. Now, here's what we want to understand. There's a notion, go a little bit bigger. In solving these problems, known as compatibility. What that means is, in order for something we know to be true in the problem statement, right? In order for something to be true, that implies a certain empirical relationship or a certain equation or a certain equating of something, right? In order for something to be true that we read, that interprets or that translates to a way that we can then represent it mathematically. And the thing I want to point out in this case that gives us a clue for compatibility is this part of the statement right here. It says, so that the beam remains horizontal in a horizontal position when it is loaded. What that tells us is when this beam is loaded, or when these rods are loaded, when this beam is loaded and these rods begin to displace, this beam, this horizontal beam, is going to remain straight, which tells us that the displacement in rod CD and in the rod AB is going to equal each other. Make sure you see my face, all right? Make sure y'all with me on this. It means that in order for this to stay horizontal, as it is loaded, that the displacement in this rod and displacement in this rod is going to have to be the same thing. So let's come back over here and write that mathematically. It means that the displacement in rod AB, delta sub AB, is equal to the displacement in rod CD. And that, my friends, is what we call a compatibility equation. Compatibility equation, right? And so what that does is it allows us, it unlocks for us greater understanding as we try to solve for these particular things. Well, what are the equations? We know what the equations are in this case. AB is basically the force AB times the length of AB over the area of AB times the modulus of elasticity of AB equal to F CD times the length of CD over the area of CD times the modulus of elasticity of CD. So we're in luck for a couple of things, right? We are in a good position for a number of things. When we look back at our problem statement, we see that both steel beams are of the same material, A36 steel ties. So that means that E, the modulus of elasticity, will be exactly the same. And so we can go ahead and cancel these out. Another thing that we see are exactly the same is the length of these beams, the length of these rods, rather. The length of these rods are both 6 feet. So we can go ahead and cancel that out. We already know that FAB and FCD are different. Fortunately, we already found that here. What about the area? Well, the problem statement tells us it doesn't say anything about area. It doesn't say anything about area at all. So it's important for us to leave that there and then maybe just write this as the equation for area. Pi times D squared over 4. And because this is AB, we'll say D sub AB. And then this equation is also pi DCD squared over 4. So in this case, there are two unknowns. There's the diameter of rod AB and the diameter of rod CD, because we already know these. We already know these values. We should be able to rewrite these. If we plug in our values, you should be able to rewrite these mathematically to equate to 9, because FAB is 9. Because that cancels out, So FAB is 9 over DAB squared equals 3 over DCD squared. Or in other words, the square root of 9 CD squared is equal to the square root of 3 DAB squared, cancel out squares, which would leave us with 3 DCD equals the square root of 3, not deterministic in terms of a whole number. So we'll just leave it as square root of 3 on DAB. You all follow me along? I hope you're following along with me. So we multiplied DCD squared times 9 to get that on that side, DAB squared times 3 to get that on that side. And then we took the square root of both sides. Square root of 9 is 3. Square root of DCD squared is DCD. Then the square root of 3, we just left it as the square root of 3. And square root of DAB squared is just a DAB. So this is where we are now as a relationship between DCD, one unknown, and the other unknown, DAB. Now, we have two unknowns, but we know that this particular relationship, again, just to remind you, makes it compatible such that the rod stays horizontal when it is loaded, right? And these are what we have to solve for. It's just the smallest diameter of each rod so that the beam remains in a horizontal position. So the next thing that we need to do is find out what's going to give us the smallest diameter. Well, we were given another piece of information in our equation. I didn't realize that wasn't there, so push this up so you can see it. Another piece of information we were given in our problem statement was that the allowable stress is 16.2 KSI. So in order to get the smallest diameter, what we need to do is set equal to this allowable stress, the equation for stress, which is F over A. F over A. Well, the diameters are going to be in this area here. And then the forces that we already found is what we can use for F over A. So the question you might ask here is which F and which A? Well, the answer is we just pick one. We just pick one because we already have a relationship between the diameters here. So once we can solve for one diameter, we can solve for the other. So we'll say here that 16.2 KSI is equal to, we'll go with AB. FAB is 9 over pi d squared DAB over 4. That's the only unknown. If we solve for DAB, we would get a value of 0.841 inches. And because we know the relationship DAB has with DCD, we can plug that in there and find that DCD is equal to 0.486 inches. These are our diameters, or AKA our answers for this problem. And we could have did this the other way around. We could have put DCD here, right, and solve for it. We would have gotten this value, plug that value in there, and then get this value. So I hope you all follow along. The new concept, again, that this particular problem allowed us to identify is this notion of compatibility equations. And that's going to be important because we're going to have a number of other examples. We're going to probably do another one here, but also in your homework, in your assignments at home, you're going to find where compatibility equations are necessary. Now, this next problem 4-31 is what we're going to look at now. 4-31. Let me see if we can get an image on the screen. Problem 4-31. And this is right here. Here's 4-31. Share my screen for you. The problem statement tells us that this column is constructed of high strength concrete. So the silver part there, the gray part is high strength concrete, and A992 steel reinforcing rods. So all of these dots here are steel rods. If the column is subjected to a 200-pound kip axial force, determine the average stress in the concrete and each rod, right? Each rod has a diameter of 1 inch diameter, 1 inch diameter. So here's what we want to start off by doing. We want to start off by writing our equation in terms of equilibrium, we know if we sum the forces in the y direction, up being positive, let me just show this right here, this free body diagram. 200 kips here. Then we have a resistant force of the concrete and a resistant force of the rods. Let's say steel, PST. So that means that some of the forces in the y direction is P concrete plus P steel minus 200 equals 0. Now, this is a point where we bring out another compatibility equation. Because if we look at this image, we see that this is a concrete column with steel rods in it. And they are what we call a composite material, meaning it's a composition of materials that is acting as one material. So one of the things that we can know in terms of compatibility is when one deflects, or the displacement of the steel is going to be equal to the displacement that takes place in the concrete. Is that fair? That's in order for this to be compatible. In order for this to act as one, it's going to have to experience the same amount of displacement when this 200-pound or this 200 kip force is being applied. So now we need to just begin to write our equation. What is the displacement of steel? Well, it is the force in the steel times the length. What is the length? 3 feet. Let's convert that to inches. So 3 times 12 over A, the area of the concrete, or the steel, I'm sorry, the area of the steel. Let me come back to that. And then we're going to show the modulus of elasticity of steel. Well, here's something that isn't in a problem statement that I want you to take note of. When we're talking about your typical steels, this is one that you can remember. The modulus of elasticity of steel is 29,000 KSI. Right? Take note of that. Unless otherwise given in this course, you can assume that when you're talking about steel, the modulus of elasticity, the E, is going to be 29,000 KSI. Now, when it comes to the area of the steel, keep in mind, again, at the top, we see a cross section like this, and then we have eight rods here. So that means that the area here, first and foremost, is the diameter, pi times the diameter squared over 4. Diameter in this case is 1. What did it tell us? Is 1. Oh, no, it has it in the image right here. The diameter is 4 inches, or the radius is 4 inches. So the diameter is 8 inches. So I can go ahead and write that as 8. So remember that. That is the area of the entire cross section. But from there, we're going to need to subtract 8 times the area of those individual rods. Eight times the individual rods. And so we could actually calculate that right now, right? Pi times 8 squared divided by 4 minus 8 times pi 1 squared divided by 4. So this area right here is equal to 43.982 square inches. Right? So we have our equation here, P L over A E, and set that equal to the equation for the relative displacement in the concrete. The relative displacement in the concrete. quick mistake I just noticed. So in here, this case, I gave you the area for the concrete. That's not the steel. So this is not correct. The area of the steel is actually easy to determine by simply looking at this part right here. So the area of the steel can just be pi 1 squared over 4. All right, so this is actually the area of the concrete. All right, as I just explained it here, I gave you the cross-sectional area, then I subtracted the area of the steel. Lost track that this side is looking at the area of the steel, which is just this part. So this comes over here. So P concrete times the length, 3 times 12, over the area of the concrete. And that is what we calculated here. The area of the concrete times the modulus, elastic modulus of the concrete. Now this will vary a little bit for this particular problem. The answer is 4.2 times 10 to the third. All right, hope you all follow along. So again, go back and watch it. Look at how we basically took the cross-sectional area of this entire column, subtracted the 8 steel rods. So that gave us the accurate area of the concrete. The area of the steel for 1 steel rod is just simply here, right? We're able to put that here. And if we did the math on here, right? If we did the math, we will be able to determine that the relationship between P steel and P concrete is P steel is equal to 0.1233 P concrete. All right, this is where we are so far. So go ahead and pause if you need to. Go back and make sure that this is appropriately applied to the right area of concrete. This value we calculated, and that you also get the right area of steel over here. And you should land on this relationship between P steel and P concrete. And once you find this relationship, now you have 2 different equations you can use. You have this equation and you have this equation to be able to solve for P steel and P concrete. And by doing so, you would find that P steel is equal to 12.41 kips, and P concrete is equal to 100.68 kips. All right, both of these are in kips. But what does the problem ask us for? We are almost there. It gives us the force in these respective materials, but it asks us a different question. It says to us, what is the average normal stress? Well, that should be pretty straightforward because we know that the average stress is equal to force over area. So the first thing we could easily do is by putting for the steel, P steel over area of steel equals 12.41 kips over the area of steel. We got area of steel here is pi 1 squared over 4, 0.7854, 0.7854 inches. And so the average is here is 15.8. Next, if we were to do the same thing for the stress of the concrete, we would have a value of 100.68 over this value here that we found out, 43.982 square inches. And for your average shear stress, 100.68 divided by 43.982. So you have a value of 2.29 KSI. So these are our values that we need for our answers. Apologize for having that too low. Hope you all can see that there. I'm gonna leave that there for the time being. So that's going to conclude this particular lecture. What I think I will probably do is a separate video a little later to do just a couple of more examples of these. These are the concepts that you need to know, pretty much everything you need to know when it comes down to axial deformation and loads. The only thing that I would say that we could look a little bit more at, and we'll bring up later, are the compatibility equations, right? Being able to identify how you can apply certain boundary conditions and equations to help you unlock the certain equations you need in order to solve for these type of problems. So we'll stop here. I hope this helps you keep going on your assignments, and I'll catch you on the next video. Peace.